talk about the situation where we have a spring, a mass connected to it, first on a frictionless surface. So let's put this on a horizontal surface. The mass on the spring. Now, if this were the equilibrium position, I'm going to define equilibrium as my S equals 0. So if you remember, we said the potential energy stored by the spring is 1/2 Ks squared. Our author writes this as 1/2 K delta S squared, which is the same thing when I define S as 0 at equilibrium. Delta S always means how much the spring is stretched or compressed from equilibrium. By defining equilibrium as S equals 0, defining delta S equals 0 is what allows me to just say S is equal to delta S, because my either initial or final is always 0. That's how I get away with that. Now, sitting at rest like this, the total energy in this system at the moment is 0. The spring's not storing energy because it's not stretched or compressed. The mass isn't moving, so there's no kinetic energy. Since it's a horizontal surface, if we call down here y equals 0, then gravitational potential energy will always be 0 because the mass stays on the surface. To get the mass to move, to add energy to the system, I can either pull the mass to the right or push the mass to the left. So let's say I push the mass to the left. So now the spring is compressed by some distance. I'll call this an initial. By compressing the spring, I have done work. So I had to apply a force and move that block a distance of S initial. So my work gave this spring mass interaction some potential energy, simply because the spring is now compressed. It is pushing on the block. As soon as I release the block, the spring's pushing on it and the block will start to move. But at this exact moment in time, the block is not yet moving, so there's no kinetic energy. All right, so the total energy of the system is the potential energy in the spring. That was determined by how far I personally pushed the mass to the side, which in turn is how far the spring ends up being compressed. Well, we know if we release it from rest, the spring is pushing on the mass, so the mass will be moving. The spring will not be stretched quite so far, so I'm measuring the stretch or compression of the spring from where it connects to the block to equilibrium. So at this moment in time, the spring still is compressed. It's not compressed as far as it was initially. So this is smaller than part 1, if this is part 1 up here. So S is smaller than S initial. The spring is not compressed as far, so the potential energy it has is a bit smaller. Well, that potential energy is turning into or transforming into kinetic energy. This total energy is the same. So again, I said, let's imagine a frictionless surface. So there's no other form of energy that is resulting here. We could look at any given moment in time. If we look at the moment where the mass has gone as far as it can to the right-hand side, so that its speed is 0 again, we know the spring is stretched to some S final. So there is energy in this spring. But if we're talking about the moment the mass is not moving, there's no kinetic energy, this total energy has to be the same as those previous steps. So conservation of energy allows us to look at the energy at any individual, any 2 points in time and compare them. If we compare this top moment in time, so moment 1 to this moment 3, the 1/2s cancel. The K is a constant. This given spring will have a specific spring constant. We find out that the magnitude of S initial is going to equal the magnitude of S final. The mass will travel the same distance on the other side that it was compressed initially. So I pulled a picture from your book. This is another energy diagram. Energy versus position. Here they're labeling it position as X because they're talking about a mass oscillating on a horizontal surface with the spring. This horizontal line represents the total energy. If you think back to this setup with the mass on the spring, if I am the one pushing the mass to compress the spring, I am the one determining this total energy. So this is, I guess it says up here. The height of the total energy line is determined by how far you stretch or compress the spring. So that initial stretch or compression, when all of the energies in the spring itself, stored because of the spring mass interaction, however far we compress or stretch the spring is going to determine how much energy is in the system. Because at this moment in time, there was no kinetic energy, and thus the total energy is determined by that initial compression or stretch. On this graph, they called the equilibrium point L0. The way I've been defining it, I'm calling our equilibrium point S equals 0, or a position of 0. So anything to the left would mean a negative displacement, anything to the right would be a positive displacement. But conveniently, in our potential energy term for springs, S is squared. So plus and minus actually doesn't even matter when we're calculating and accounting for the energy of the spring. Similar to the ball toss problem, at any stretch or compression, anything going up to the curve, this potential energy. Now, the curve is a parabola because it's representing this 1/2 ks squared. At any given moment in time, the height above the potential energy curve represents the kinetic energy. And at this point, there's no kinetic energy because it's all potential. So similar to the mass on, the ball being tossed, all we're doing is we're seeing a transformation of energy between potential and kinetic, back and forth and back and forth. Now, if we had a mass on a spring, but it was hanging the equilibrium would be when this mass spring system is at rest. I would call this S equals 0. To give this system energy, I would either need to pull the mass down, stretching the spring out, or I could lift the mass and cause the spring to compress some. But either way, we have to get some energy into the system. Anytime we are working with springs, we need to represent where the equilibrium position is located, because the spring potential energy, when we say 1/2 ks squared, S is always measured from equilibrium to where the mass connects with the spring. So if I pull this mass down, I can definitely say there's spring or elastic potential energy because the spring is stretched. So there's energy within this system, this mass spring system, simply because the spring is now stretched. If I let the mass go, I know this mass is going to start moving upwards. So at some moment, it will have this upwards velocity. I'll just call it a final. The spring is still stretched, so S final. But now we also have a change in height, which means we need to account for gravitational potential energy as well, right? Gravitational potential energy, mgy, I apologize for my email notifications. I forgot to close my email app. Kinetic energy if the mass is moving. Okay, so in the spring, S is always measured from the equilibrium. With gravitational potential energy, Y, we can define Y equals 0 wherever we want. So if we want Y to be 0, for example, if it's confusing, if we want Y to be 0 at equilibrium as well, then we would need to say in this initial, when I've pulled the mass downwards, stretching the spring, we would need to say the gravitational potential energy, mg y initial, where y initial is negative, S initial. So negative mg S initial. Now negative really just goes back to a coordinate system. Having negative gravitational potential energy just means there's less energy than at 0. So we don't have to stress too much about that. The kinetic energy initially is 0. So initial means this situation. I've pulled the mass down. It has stretched the spring. All of this energy together represents the total energy of the system. We would say the total energy is 1/2 k S initial squared minus mg S initial. if there's no external forces, then that total energy needs to stay constant. So as this block is moving upwards, we now have kinetic energy. We have less energy stored in the spring because S final is smaller. We have more gravitational potential energy. Y is going to be this S final. At this moment in time, we have a total energy that consists of gravitational potential energy, elastic potential energy, and kinetic energy. But this total energy has to equal this total energy. And that's true even when the mass gets up to its maximum height, above equilibrium. At its maximum height, the speed would be 0. So at this point, we would say the kinetic energy is 0. The spring energy is 1/2 ks squared, where S is this, height above equilibrium. Gravitational potential energy, mg, y final, where that's the same as S final, if we're calling y equals 0 at equilibrium. Conservation of energy is really nice because we can just talk about this concept of energy at these given moments in time that we care about and build our conservation of energy equation to work from there. Having friction, we're just going to have thermal energy. If there's any external forces, we would account for those as well in terms of the work external. So I'll do some examples for you to follow through and hopefully get a better idea of how to use this process.